when we take first course in abstract algebra, a normal subgroup. This is something I did like 4 or 5 years ago, maybe, or maybe more, but I don't remember I ever talk about it. So I thought I share with you this, what's all this about. Okay, so let's start with the definition here. Like you have a semigroup and you have D is a set that live inside this semigroup, and you choose an integer n bigger or equal to 2. So what do we mean that this set is enclosed? Exactly what you expect. Whenever I select n element in D, then I want the, if you want to call the operation on the group star, this star depends on the group, could be addition, multiplication, or something you define. Then A1 star up to AN lives in D. So definitely, if you let N, or whenever we mention D is closed, in a natural way to define it, that whenever you have A and B in the group, then you have A star B to be in D. So definitely a closed set, now using this definition, you call them two closed set. But let's look at this concept here. Here I mentioned some examples. Like if you take the set of all odd integer and you define the normal addition on D, then definitely odd plus odd is not odd. All of us know that. So definitely this set is not 2 closed. However, it is 3 closed. Okay, and 3 I think here is the minimum. What about if you take this set, 1, 4, 7, 10, and keep going? Then definitely this set K under addition, normal addition, is 4 closed, but definitely is not 2 and is not the 3. Okay, so these n-closed set, it seems like, maybe it's worth the time to look at them. We always look at 2 closed. Okay, so again, I'm tell you what is, where did I use these n closed subset. Here is it, the comment. If you read, the main result that if you have a subgroup of a group and the index of H inside the bigger group is n less than infinity, and remember the index here, all of us learned that the number of all distinct left coset of the subgroup H inside the group, the bigger one. Then I was able to characterize normal subgroup in terms of n closed set. So the main result, again, if the index of H and G is equal to n less than infinity, then H is a normal subgroup if and only if every left coset is n plus 1 closed subset. When you look at that, it's kind of, uh, when you see the proof, I think it's technical. It's not completely trivial and it's not completely hard. It's trivial. Whenever I go back and think about this question, this is remind me that what do we mean with the difficult? The difficulty here, if there is a difficulty, why somebody want to think about that. As soon as you start thinking about that, just like many things in math, things collapse. Okay. Uh, of course, here I'm giving you definition, which I already mentioned. If we have a subgroup, H not equal to the whole group, then I mentioned the index, and I mention here notation what I mean A to the N, mean A star A star A N times. So if the star is addition, then A to the N mean A plus A plus A and so on. And AN inverse, this is just the inverse of AN. And as usual, the absolute value of A mean the order of the element in the group, the smallest positive integer where you have A to the N equal the identity. And of course, if you have elements D1 up to dk in D, then what do we mean with that? Just exactly what you expect. It means D1 star D star dk star D, where D is an element in the group. R and Q and Z will be just the, the normal, the set of integers, rational and real. Okay, here is some result. If you read this result, uh, kind of interesting. If you let D to be a finite subset of a group, and assume D is not too closed. Well, because, all of us know if it's too closed, then it will be subgroup. So I assume D is not. And for some integer n bigger or equal to 3, I know that D under the same operation n is enclosed. Then I can construct subgroups of D. How? Remember, D is not subgroup of the bigger one. Just choose randomly D1 up to Dn minus 2 element in D and form this set here in 1. D1 star, then this become a subgroup. Okay? If you look at number 3, what does it say? That D to the n minus 2 star D is the same as B to the n minus 2 star D, okay? For every D and I don't know what, yeah. And that's equal D1 star, Dn minus 2 for every D, B, or these things in D. Number 3. They have to be equal. Okay. Well, if you have a finite group and you have a subset D inside the bigger group, and you suppose that D is not too closed, meaning it's not a subgroup, and assume that for some integer n bigger or equal to 3, D star is enclosed, then the conclusion that D to the n minus 2, meaning D star D star D n minus 2 times, and then star D, the bigger D, this is going to be a subgroup. And here I gave you an example where finite is needed. The following example show that the hypothesis D is finite is crucial. Why? If you take the bigger group to be Z, and D to be just the set of odd numbers, then definitely D is a 3 closed. So now, if you look at the result, you have in I should have D to the n minus 2 star D to be a subgroup. But here, um uh, n is 3. If I do A3 minus 2 plus D, which is 1 plus D, and this is under addition, is not definitely a subgroup. So definitely this example show that the group finite is crucial. Okay? And here also you can because I gave a result on a group, in fact, you can talk about subgroup. If you have a semigroup and D is under the same operation is any closed subset, then this condition D1, star Dn minus up to Dn minus 2 star D is two closed subset. Okay? Um, Here is one that I think that will help me to give you the main result that I mentioned at the beginning of the talk. Because remember, my goal to show that if you have a subgroup from a bigger group and the index of this subgroup inside the bigger group is finite, then this subgroup will be normal if and only if every left coset is n plus 1 closed subset. Okay, so here we selected H to be a subgroup, and I selected a left coset A star H. This is a left coset of the uh, then is an N L, remember what is L, is the left coset, is an N closed subset. Also, I assume that, and I assume K be the least positive integer where L star is K closed. So I already know that L is N closed, but I'm selecting the smallest positive integer where L star is K closed. Okay? Then we have the following, that A to the n minus 1 has to be an element in H. A star H equal H star A, which is equal L. Okay? And that's somehow what I need here. And you can look up at number 3 and look at number 4. If A to the m is in H, if and only if K minus 1 is a factor of m, okay? And L star, this left coset, is an M closed for some positive integer if and only if M is equal to C K minus 1 plus 1 for some integer C bigger or equal 1. Let's look at number 5 again. Remember, L is a left coset, and I already know that L is an N closed subset. I already know that. It's given. And K is the smallest positive integer where this is true. Then I gave, you can describe all the M where L stay M closed. M has to be C times K minus 1 plus 1. Okay? So we know exactly, if you know the smallest positive integer, then we know all the m's where L stay M closed. Okay, uh, here is another result that follow from the previous theorem. If you have a subgroup and you have a left coset, then L star is enclosed if and only if A star H equal H star A and A to the minus 1 is in H. Okay? And this is like, tell you, like in a way, uh, that your H has to be normal. Because all of us learned in the first course in abstract algebra, uh, when a subgroup is a normal subgroup, whenever every left coset is the same as right coset. Okay? I'm not gonna, I just thought I share these ideas with you. Let me see if I have time. Uh, Here also some technical things going on. Okay, here is I gave an example of any closed set. Like you take a group with at least two elements and A be non-identity element of the group. And you assume the order of A equal K. Okay, then definitely this set A is M closed whenever you have M to be BK plus 1. That's a trivial example of M closed set. Okay, here also another example. It is possible to have a group and a left coset such that for some positive integer n, a to the n is in H, and a to the n plus 1 is in L for every a in L, but L is not M closed subset for every integer m bigger or equal to 2. And here is the example. If you take the permutation S3 and you take H, this here, this is a subgroup, and you take this element 1, 3, which is not in H, and you form this left coset, if you get A to the 6 here, remember A here is 1, 3, this cycle 1, 3. A to the 6 will be in H, and A to the 7 is in L for every A in L. Okay? So in fact, A here is not just the cycle 1, 3, is for every A in L. But we know that this left coset is not equal to the right coset. So that means L is not an M closed for every integer m bigger or equal to 2. Okay? And then another example here. It's possible that a subgroup and you have a left coset where these are equal, but L is not enclosed for every n bigger or equal to 2. And so the question is why? The reason, because remember the theorem I promised with, we have one condition that the number of the left coset to be a finite number. So if you have a subgroup like an infinite where the index of this subgroup inside the bigger group is infinite, then you will have this problem. And here is the example. If you take R under addition, and definitely Z under addition is a subgroup of R, if you take L to be this left coset, but definitely L under addition is not enclosed for each integer n or equal to 2. So this example also show that the number of the left coset finite is needed in the result. Okay? Yeah, I think I stop with this theorem here, the last one I promised with. That if you have a subgroup, remember here is the thing, the group could be infinite, but what I need, the subgroup to have finitely many left coset, the index of H inside the bigger. Then H is a normal subgroup if and only if every left coset is n plus 1 closed subset of the bigger group. Okay? All right. I mean, I thank you. And why did I do that? Maybe some student or can investigate more about these enclosed, because usually whenever even we study rings or we always look at things in terms of two closed. What about like enclosed? Because I mentioned earlier there are some set that are not enclosed, two closed, but they are 3 or 4 or 5. So what I mean, can we use these set to like give some result, or I don't know what you can do with it. Like here, as I told you, I only have this paper on this enclosed, and I never studied them after that. But I thought this is kind of interesting for for maybe like a general talk, because I think maybe they are a statistician here and applied and a student and so on. Okay, I think I stop here, and I thank you and I thank the organizer.
Thank you, sir. Thank you, Professor Ayman Badawi. I think this is very, very beautifully and very nicely you described your problem. I think this is very much useful for our student and the participants, those who are here. So I request all the audience, those who are interested to ask them if they have any query, then ask from Ayman Badawi.